Hello and welcome to this lecture on fundamentals of electric drives. In the last lecture, we were discussing about the effect of harmonics on the operation of induction motor. We will continue from that. Now, we have seen that the effect of the harmonics is to increase the losses of the motor and to add to the pulsating torque. However, there is no contribution for the average torque. So, the average torque is very small. So, the harmonic does not contribute to any average torque. Now, how do we calculate the total current of the motor when the motor is supplied from a non-sinusoidal supply? Now, the total current will consist of the fundamental current plus the various harmonic components. So, we see the total current of the stator in the presence of harmonics is IRMS. So, IRMS of the stator current square is equal to the fundamental component. So, we can say that we have IS1 let us say plus various harmonics. So, we can say that M is equal to 3 to 3, 5, 9, 11 and so on. So, this is I m square. Now, the stator can have two possibility. The stator can either be delta connected or it can be star connected. Now, if we have a delta connected stator, if the stator is delta connected, which means the windings are connected in delta, so this is delta connected stator. So, the stator currents will consist of all odd harmonics, because there is a possibility of the triplet harmonic also to flow. So, this is the path of the triplet harmonic, they will circulate in delta. So, the triplet harmonic can flow in the delta connected winding. Triplet harmonics can flow in a delta connected stator. So, we have the current which has got all possible harmonics, the third harmonic, the ninth harmonic, the 15th harmonic, all these harmonics will also be present along with the other odd harmonics. Now, if the stator is star connected, there is no path for the triplet harmonic to flow, because the triplet harmonic is cophasal. So, they require a neutral path. So, in the absence of the neutral connection, there is no path for the triplet harmonic to flow in a star connected stator. So, if the stator is star connected, stator. So, what we have here, the harmonic, the RMS current square is equal to the fundamental will anyway be present, RMS value of that, plus the sum of the harmonic components, and these harmonics would be 5th harmonic, there will be 7th harmonic as well here, the 7th harmonic, 11th harmonic and so on. The triplet harmonic cannot flow in a star connected stator, or triplet harmonic current are absent in a star connected stator. So, we have to draw the harmonic equivalent circuit for each harmonic and find out the corresponding harmonic components and take the square and then the square root, we get the total harmonic current. So, this current is definitely higher than the fundamental component, that is why these currents will increase the losses of the motor. Motor losses will increase, efficiency will go down. So, the motor has to be derated. So, derating of the motor is required, derating of the motor is required. It means the motor cannot supply the rated power because of the increased losses, and then there is torque pulsation. Torque pulsation due to the interaction of, let us say we have the 7th harmonic, the 7th harmonic rotates in the forward direction and the 5th harmonic rotates in the backward direction. So, these harmonics will interact with each other to produce pulsating torque. So, the torque will be pulsating and this will also be interacting with the fundamental component to produce the pulsating torque. So, this will give rise to the noisy operation of the motor. Now, let us try to see the operation of induction motor from unbalanced supply. When the supply is not balanced, we are assuming that we have the 3-phase stator which is supplied from a balanced 3-phase voltages, but very often the supply voltages are not unbalanced, are not balanced. So, if the supply voltages are unbalanced, what is the effect of unbalanced supply voltage on the operation of induction motor? That we will be discussing. Operation of induction motor with unbalanced voltage. Now, we have the stator of the induction motor and this motor is supplied with a unbalanced voltage. Let us say we have phase A, B and C, the neutral here, but the voltages are not balanced. So, if the voltages are not balanced, what happens? We have the supply voltages which are not exactly shifted from each other by 120, the magnitude may not be the same. So, we have the different voltages here. Let us say we apply with something like V A, this is V B and this is V C, and this is unbalanced supply. So, when the supply is unbalanced, what we can do here, we can split this into 3 different sequence component. We can split this into a positive sequence component, this is V A or V P A, this is the positive sequence component of phase A. So, this is positive of phase B, this is positive of phase C, and we can split this into a negative sequence component, negative of phase A and negative of phase B and negative of phase C, and a 0 sequence component. Zero of phase A, 0 of phase B and 0 of phase C. Now, this is the positive sequence component, we have a negative sequence component and we have a 0 sequence component. Now, the original system is unbalanced. So, we are breaking down this into a positive, negative and 0 sequence component. So, we can write the voltage equation that the voltage V A is given by a positive sequence component, a negative sequence component of phase A and a 0 sequence component of phase A. Similarly, we have phase B. Phase B is found out by a positive sequence component of phase B, the negative sequence component of phase B and the 0 sequence component of phase C. We also have phase C here. This is positive sequence component of phase C, the negative sequence component of phase C, the 0 sequence component of phase C. Now, if we notice here that the positive sequence component, here we have A and B is lagging behind A by 120 and C is lagging behind B by 120. So, the sequence is ABC, but in the negative sequence component, this is phase A and phase C is lagging behind phase A by 120 and phase B, which is here, this is lagging phase C by 120. So, in this case the sequence is ACB, not ABC, but ACB. But for the 0 sequence component, all the phases are having the same phase. So, this is cophasal. This represents the cophasal set of vectors. Now, if we see this a negative, positive and 0 sequence component, we will try to replace this only in terms of phase A here. So, phase B in this case we have PB. So, we can just write down alpha square into PBA, because this is rotated by 240 in this case. So, what is alpha here? Alpha is an operator which is given by exponential j 2 pi by 3. This is basically an angle which is 120 degree. This is equivalent to, we can also write down this as 1 angle 120 degree. So, alpha is an operator which is just angle 120, is rotation by 120 degree or exponential j 2 pi by 3. So, in this case if we rotate this by 2 pi by 3, we get what is PB. Similarly, plus alpha positive into A, this is the negative sequence component. So, that is phase B here. So, phase B can be obtained by rotation by only alpha. So, this is N A plus this is 0 A, because 0 A, 0 V 0 B and V 0 C are the same thing. So, in this case we just have to write here they are all equal. So, in that case we will say that V 0 A, V 0 B and V 0 C are the same. So, V 0 A is same as V 0 B is same as V 0 C. Now, the third equation in this case is alpha V P A, that is for V C, plus alpha square into V N A plus V 0 A. So, from this equation we can ultimately find out what is the sequence component V P A, V N A and V 0 A. So, we can find out finally what is the sequence component voltage V P A and V N A and V 0 A. So, from the set of equation that we wrote here, this three set of equation, we can readjust this equation and ultimately get the values of the individual sequence components. So, this is equal to 1/3. If we simplify this, we get the following values here: 1/3 of V A plus alpha V b plus alpha square V c, and the negative sequence component is 1/3 of V a plus alpha square V b plus alpha V c, that is equal to the 0 sequence component is equal to 1/3 of V a plus V b plus V c. Now, what we have tried to do here is the following, that we are having a set of unbalanced voltages. So, when we are having a set of unbalanced voltage, we have no direct clue how will this unbalanced voltage will affect the operation of induction motor. So, by taking the help of sequence components, we can break down this unbalanced voltage V a, V b, V c into a positive sequence component, a negative sequence component and a 0 sequence component. And the respective sequence component can be obtained from these 3 equations. So, we have, this is for the positive sequence component, V a plus alpha into V b plus alpha square V c. The second equation gives us the negative sequence component, 1/3 of V a plus alpha square V b plus alpha V c, and the third equation gives us the 0 sequence component, which is 1/3 of V a plus V b plus V c. Now, these are the 3 sequence component voltages which are applied on the induction motor. Now, since we assume that our system is a linear system, we are ignoring the effect of saturation. For the time being, we can apply the principle of superposition. It means we can apply these voltages independently and find out the effect of positive sequence voltage on the operation of induction motor, then negative sequence component voltage on the operation of induction motor and 0 sequence component on the operation of induction motor. Now, we know that the 0 sequence component does not produce any torque. So, we can directly eliminate the 0 sequence component and only discuss about the positive and negative sequence component. So, this sequence component, 0 sequence component does not produce any torque because there is no rotating field. So, we will not be considering about the 0 sequence component, we will take the positive sequence component and the negative sequence component while starting the operation of induction motor. Now, let us see the positive sequence component. So, if we apply the positive sequence component voltage, we have the same equivalent circuit. The equivalent circuit consists of the resistance, the reactance of the rotor and the resistance of the rotor. So, what we are applying here? V p, and this is our phase voltage. So, this is the stator resistance, the stator reactance, the rotor reactance and the rotor resistance, and this slip is the positive sequence slip, that is S p. The positive sequence voltage is responsible for a positive sequence field. So, the synchronous speed here is for the positive sequence component is same as omega m s. So, what is the slip here? The slip in this case is omega m s for the positive sequence component minus omega m by omega m s for the positive sequence component, and since omega m s p equal to omega m s. So, that is omega m s minus omega m by omega m s. So, the positive sequence slip is same as the normal slip of the induction motor. So, we can derive the rotor resistance, the rotor current here, that is IRP for the positive sequence component. So, IRP is given by Vp divided by Rs plus Rr prime by S plus J into Xs plus Xr prime. What about the torque here? The torque is given by 3 into IRP whole square RR prime by S by omega ms. This is the torque for the positive sequence component, that is equal to Vp square divided by Rs plus RR by S whole square plus Xs plus Xr whole square 3 by omega ms into RR prime by S. So, this torque is positive. What about the effect of negative sequence component on the operation of induction motor? So, we apply now the negative sequence component. So, we apply the negative sequence component voltage, we have the similar equivalent circuit here, but our sequence component is negative. We apply the negative sequence component per phase value. This is the resistance, the reactance of the stator Jxs, the reactance of the rotor, and here the rotor resistance divided by the negative sequence slip. Now, what is the synchronous speed of the negative sequence voltage? The negative sequence rotate in the opposite direction that of the positive sequence field. So, the synchronous speed here is minus omega ms. So, the synchronous speed here is minus omega ms. So, if we find out the slip for the negative sequence component, that is the negative sequence component synchronous speed omega sm n minus omega m divided by omega sm n, that is equal to minus omega ms minus omega m by minus omega ms, that is equal to omega ms plus omega m by omega ms. We will do some readjustment here. We will take here 2 omega ms minus omega ms minus omega m divided by omega ms. So, if we simplify this, this gives us 2 minus s. So, the slip of the negative sequence component voltage is 2 minus s. So, we can find out the current here, the current for the negative sequence component, that is the rotor current for the negative sequence component is the negative sequence component voltage divided by the resistance Rs plus R prime by 2 minus s here plus j into Xs plus Xr prime. So, by applying the negative sequence component method, the slip can be found out, slip is 2 minus s. So, by having that slip we can find out the current. What about the torque here? The torque is given as before, the torque of the negative sequence component is 3 by minus omega ms, because that is the synchronous speed, into I r n square into r r by s n. So, that is minus 3 omega ms into V n square divided by R s plus R r by 2 minus s whole square plus X s plus X r square into R r by 2 minus s. So, we observe that the torque for the negative sequence component is negative, because the field is rotating in the opposite direction, torque is negative. So, if we draw this in a torque speed characteristic, we will see the following, that this is our speed versus torque, speed in the y axis and torque in the x axis. So, we have a positive sequence voltage, which is this, Now, we also have a negative sequence voltage for which the speed is the synchronous speed is negative, here it is plus omega ms, and we have minus omega ms here. So, the negative sequence voltage will have its own torque. So, this is the positive sequence voltage or the positive sequence torque, which is T p, and the negative sequence torque is negative here, which we can call as T n. So, what about the total torque? Because the motor has got only two torques, T p and T n, the total torque is the sum of these two torques. So, if we sum these two torques, we get the overall torque or the net torque, which is the sum of these two torques. So, the net torque is given like this, it is somewhat reduced from the original one. So, this is the net torque. So, this is the net torque. So, the net torque T is given as T p plus T n, which is the sum of these two torques, the negative sequence torque and the positive sequence torque, which is given as the net torque. So, the net torque is reduced. So, it means in case of an unbalanced voltage supply, the net torque is reduced and hence the net power is also reduced. So, the unbalanced voltage result in reduction of the torque of the net torque and also the reduction of net power, reduction of net torque and reduction of net power. So, this is what we can conclude by having this analysis. So, in this lecture we have seen that if we have an unbalanced supply, we can break the supply into a positive sequence component, a negative sequence component and a zero sequence component. The zero sequence component does not take part in torque production. The positive sequence component will lead to the positive sequence torque, which is positive. The negative sequence component of voltage will lead to negative torque production, because that results in a rotating field in the opposite direction. The net torque is reduced. Since the net torque is reduced, the net power is also reduced, and hence when there is unbalance, the motor cannot supply the full power. So, we have to go for the derating. The motor is derated due to unbalanced power supply, due to unbalanced voltage, the motor is derated. So, this is the effect of unbalanced voltage supply on the operation of induction motor. So, we conclude for today's lecture, we will continue in the next lecture.